You can go ahead, Sam. Thank you.
Yeah. So last time we were talking about we ended up talking about p-values and just the point I was trying to make is that it's well known that p-values, when you're trying to make data, I'm using these in the context of like deciding between two distributions, p and p prime. And I was saying that p-values, many of the tests, of course, use p-values, and part of the problem is that the p-value is a probability, but it doesn't really express the probability that we are mainly interested in, which is just the probability of these two distributions being different. And instead, the p-values are based on the assumption that whatever it is that you're measuring should be different based on like the statistics should differ in distribution when the two distributions are the same or different. And if the statistics doesn't really measure anything of interest, then a p-value, for example, that's like an extreme case, but won't be useful. So I mentioned that there's other things called effect sizes, and these things exist for not just for drift, but for many different situations. When you're doing ANOVA, when you're doing there's lots of different situations have effect sizes, which kind of more closely tend to capture the magnitude of like a practical difference, and they're less susceptible to what people often call p-hacking, of basically trying to a p-value can be, or sorry, a given test can give you if you get enough data, you can end up getting like a significant difference just because the sample size is big. So, for example, I mentioned so for example, this is Cohen's D. It's it looks basically, if you're familiar with a chi-squared test, where here it looks very similar to it. You have the sample, you have basically two sample averages and then something about the standard deviations divided by 2. Whereas with like a chi-square, not a chi-square, with like a like a 2-sample t-test, there's something here that involves like the number n, the sample size typically, and because that grows, this whatever will be significant just because the denominator like gets big, or yeah, sorry, the opposite. The denominator gets small. Right. Yeah, the denominator gets small, so then this gets big, but this doesn't. This is the effect size. It doesn't have the n, so it's less susceptible to like the effect of simply having a large sample size with the same kind of practical difference. So that's the main difference between effect sizes and kind of these hypotheses. Okay. I meant okay. The thing. Okay, right. And then the other thing is that, like, usually instead of like probabilistic or like comparing a p-value to some alpha, the effect sizes usually have some kind of like a rule of thumb, like Cohen's D. It's like if it's bigger than 0.2, it's small. Bigger than 0.5 is medium kind of effect, and 0.8 is like large. So most of them have kind of these cutoffs, as opposed to just saying like it has to be, the p-value has to be below like a preset, like 5% or something like that. Okay. Okay. So far I talked about univariate tests of detecting drift, where you have the data is a single variable, either it's a binary, like a class. So for example, you have correct or incorrect decisions, and your sample is like before and after you're testing the proportion maybe of correct versus incorrect decisions. That's a binary case. It can also, of course, be that whatever the sample that the variable you're measuring happens to be binary, say yes or no, and you're testing whether the distribution of that changed, or also it could be a numeric variable, and then there's things like the t-tests or other tests for various characteristics. Okay, so now I'm going to just to mention like some multivariate tests. Here, same situation, except now, and these will mostly be these will be the input data are kind of typically numeric, although not always. So there's a few kind of typical ways to measure drift in these cases. One of the most common ones is called the Hotelling t-squared test, which is basically a multivariate kind of generalization of the student t-test, which is for changes changes in the mean, but now it's multivariate, and it relies on like a multivariate Gaussian kind of assumption. There's kind of an issue with multivariate distributions in that they're often kind of hard to characterize or characterize in distance-based ways. So there's a few kind of like common metrics that are used in multivariate, like Wasserstein, which is called earth movers distance. It's kind of a non-parametric way to measure changes between multivariate distributions. If you're familiar with it, basically the idea is like it's non-parametric. It kind of the idea is like each observation is like if you think about the univariate case, like you have like a pile of sand. Okay, you want to that's one distribution. The other distribution is the same pile of sand like somewhere else. You have to move each grain of sand, and the total is you have to move the grains of sand to make the first move into the second. That's like the distance. So that's the univariate case. Then they have a multivariate kind of a generalization of that. And there's a few Python packages that implement them, but I don't have a personal experience with them. There's another metric called MMD, maximum mean discrepancy, which is kind of kernel based, which again don't really have a lot of experience with it either. And I was looking up some non-parametric tests, but basically what they all kind of do is test distances between kind of pairs of elements in the sample, and then kind of internally between the samples, so like a internal kind of variance, and then variance between the two samples, or like the distance between the two samples. So again, there's a few tests, but again, I'm not that familiar with them. But there's this package that I looked at very briefly, and there's a few tests, but again, I don't really have a personal knowledge of them. Again, this section is like an amalgamation of a few topics. So one thing I'm mentioning here is I spoke about this in Michael Gildine's like weekly ML group. There's a way to I find this a very kind of useful technique. This is a way to say that you detect drift. You can for example by one of these tests, you can kind of decide what is the cause of the drift in terms of like what features are most responsible for the drift being measured. And since I'm talking mostly in this about kind of non-parametric tests, this is one also non-parametric technique. Uses what's called isolation forests, which are just in short, they're metrics for measuring an algorithm for measuring how anomalous a point is, a multivariate point specifically, by basically they build a random, sort of like a random forest, except instead of targeting, like try to optimize the tree to target like a class target, they do random splits in the domain of every feature, and kind of try to like chop it up so that each point is in its own kind of box or leaf. And the idea is that the fewer splits it takes to isolate something, the more anomalous it is because it's further away from other things, and because the samples, the splits are kind of random. If it's easier to separate it from other things, it's further away. So there's a score called sorry, this is just isolated forest. It scores basically each observation based on how many times it took to chop it up. And then there's this technique called Diffie, local depth-based isolation forest feature importance, which uses this and kind of goes through the features and if something is, first of all, they can detect whether something is an anomaly, and then this algorithm can basically kind of look at the tree and see how many splits it took to isolate each feature, or how many chops were along each feature to get that observation to be isolated, and then it combines them into which features are most important in making that each observation anomaly, and then you can kind of average or do some kind of average across the observations. So I wrote a blog article here, question 11 in my blog, which illustrates this and has an implementation and shows basically that this is because it doesn't make assumptions like it doesn't make it can work on, say, non-symmetric data or it can make it work on like multimodal data particularly, as opposed to, say, other anomaly scoring things like the Hall-Nobis distance, which kind of assume like a Gaussian situation. But this is very flexible and works in some of the Harvard cases. So again, the point is that we're trying to detect drift, or these are kind of drift related topics. We try to detect drift or say like why it's happening. Okay, so that's the idea of this this kind of a side topic. Okay. Okay. Actually, I didn't. I guess I didn't mention this before. This is I guess this is back. This is still on the univariate topic, but on the categorical distribution. Sorry, I guess I didn't. Before I did only multivariate. Only I did numeric before. Sorry. Or univariate. Oh yeah, sorry. Right. Okay, this was. Okay, but this was also talked about a little bit of binary cases. This is sorry for confusion. Oh, sorry. This is oh, sorry. Here I'm talking about this is not necessarily binary. It's categorical, but not necessarily binary. Yeah. Okay. So all right. Again, the point here is that if you want to detect drift, it may be because the label distribution changes, or it may be again that the feature X itself is categorical, and you want to check if it's changed. So here we're addressing the case where Y is again, this is the thing you're trying to test. It's a categorical variable again, but not specifically binary. So the examples, like I said, are like the state in which someone lives, things like that. And typically, if you're modeling this kind of thing, it usually uses what's called the multinomial distribution, which is just what we kind of think of as like a categorical distribution. But formally, it's basically there's a fixed there's a probability vector of being each category, and then there's the total number of draws basically, and then the total frequencies among the categories have to sum up to n. Okay, so that's so most of the tests are kind of based on this kind of um, this kind of um, distribution. Okay. So
Sam, a question.
yes.
So, are we saying that for one variable we use parametric test, and for not for more than one variable we're using non-parametric test?
Yeah,
Is
so
that
actually, pretty much I'm focusing on non-parametric tests. Um, Again, like a t-test isn't really an, I mean, it's a little bit of a parametric test because it uses the Gaussian distribution, but it's
Mhm.
these are all basically non-parametric tests. I mentioned just parametric distributions kind of in the sense of like like the multivariate case where usually it's hard to characterize, you know, because like multivariate distributions are hard to say like they have a density estimate, for example,
Mm.
or so it's harder to do some of the same things that you do in univariate tests for multivariate tests, which is um, but I still wanted to kind of have focus on the non-parametric situation.
And another question: what happens if you have many dimensions, many features?
Oh, you mean categorical or numeric? Or
Um, Regardless, but okay, maybe let's start with
um,
a numerical.
right. So okay. So like I said, the most common thing in numeric is the Hotelling test, which is like the multivariate kind of test of different distribution changes in the mean. Um,
Mhm.
but again, I'm not that familiar with the multivariate tests. They're usually like a little more complicated. I guess I have to extend this section of it. There's again, there's a few there's I have to kind of go into some of the details of these tests, but there is a package that implements them. Let me um, yeah, I have to. Again, I'm not very familiar with like what are the differences between some of these tests. They're
But
also
if
like a little bit more complicated
my
too.
question is more fundamental,
Oh,
so
sorry. Okay.
if it's hard to to test for difference in distribution when you have many features, then how do you identify drift? Even though it's hard.
Um, right. So, can I get back to you about that? I have to. I
Yes,
want to
yes,
look into some of these things. Um,
yes.
I think to just I'll mention. Yeah. Sorry. I apologize for that. I'll mention that like I think that most of these tests, for example, are only numeric or something like that. That's the most common case. Certainly, I think they like the MMD is because it's a kernel-based test. And the situation gets like more complicated if you're trying to if you have a mix of categorical and numeric data and you want to decide drift on them. One of the things, and this is what we were working on with can I is it okay to mention this with Prem, right?
Hmm.
Yeah, so we were working we to implement something that kind of does an individual test on each feature and then for drift, and then as opposed to doing a multivariate test which tests across all features together, testing each individual feature based on what type of feature it is, you know, categorical, numeric, as appropriate, and then and then combining those decisions into a single decision whether there has been drift significantly on across all features. So that's one approach. Um, but again, I think that yeah, they're obviously they're more complicated. The multivariate tests are a lot more complicated. Because again, you might have to account for some kind of feature dependence and things like that.
Yeah.
Sorry, that's not like that much of an answer. But yeah, I have to expand this section.
Is it related in any way to the curse of high dimensionality?
I mean, it's yeah. I'm sure it would be related because like yeah, right. I mean, I'm not sure what to call it the curse of high dimensionality because that has kind of like a more specific meaning. But yeah, I think that kind of the more dimensions there are, maybe like you'd have to like take into account how many dimensions there are, and there's a certain amount of randomness in the dimensions, the number of dimensions, or like there's maybe a certain random chance of being different in a given dimension. How to account for that? But I think that the same problems would be evident in like a low dimension case as opposed to as also a high dimension case. But I think it's simply kind of I think it just has to do more with the fact that there are more than one dimension. Rather than being like specifically a large dimension. Yeah, yeah, so I have to expand this section because it's not very comprehensive at all. Anything else?
No, thank you.
Okay, let me just talk for a few minutes, I guess, about the categorical case a little bit more.
Sam, we have just 4 more minutes, okay?
Yeah, that's fine. Yeah, thanks. Okay, so there's basically the way that typically is dealt with a categorical case is you basically you look at the vector of counts for each category and kind of compare them in a certain way. So definitely the most common thing people are familiar with is a chi-square test, which I mentioned before. It looks like this basically. When you're comparing it, you set in a lot of these tests you set like one sample is the baseline and the other sample, so x is the baseline, x prime is the observed, and it's kind of the deviation relative to x prime as opposed to some kind of symmetric deviation. So for example, so they're not symmetric, is that's what I'm trying to say. Like the statistic it looks like this, which is similar to the actually, yeah, sorry, it's over here. Chi-square test looks like this. You given basically you're comparing each observed to the baseline and then dividing by the baseline, and you have a squared deviation of that category. You sum, and then it's the square root of that. Again, it's not symmetric because it depends on which one you set the baseline. So it's a one-way test as opposed to like a two-way test where there's not one of them as the baseline. The Cohen's W is kind of the effect size analog of this, where instead of the actual frequencies, you're testing the proportions, so it doesn't reflect the actual the same thing, but just the proportions are replace the frequencies. So it's again it's less dependent on the actual sample size than again the chi-square test, which gives a p-value. Again, it's a effect size, so it has a very similar kind of cutoffs for where for how to decide. Okay, I guess I'll stop here.
Great, thank you. Any additional questions at this point for Sam?
None from me.
Okay, great. So thank you very much for joining today, and we'll continue next week.
Sounds good. Thanks, Eitan.
Thank you.